Hey, welcome back, physics fans. Physics 12, Chapter 4, Circular Motion Lesson 1. Oh my goodness, this is like attempt number 5. Reboot, lost everything, crash, interruptions. Oh my goodness. Let's try it again. And I know this inside and out because I've done it so many times in the last couple days. Here we go. Is it possible for an object to have a constant speed and yet still be accelerating? The answer is yes, and each for the last 5 times has been yes. Why? Because constant speed doesn't mean that it's the same direction. When we go in uniform circle, we're changing the direction. So velocity is changing because the direction is changing. And therefore, it must be accelerating. So we must know that circular motion is that the object is accelerating. So we want to know the direction of that acceleration. Well, if you take a look at these little videos there, we can see that the velocity is tangent to the circle. The velocity points with these little arrows to the right here, and I have the little snapshot here. This is VI here and VF here, and we need to go VF minus VI to get the change in velocity, and the change in velocity over time is the acceleration. So the direction of this is the direction of the acceleration. So we need to subtract, but we don't know how to subtract, so we add a negative. So the negative VI is this way. So we add a negative VI to this. So the total is kind of like that. Now, do we put the total at the beginning or at the end? Well, we actually put it in the middle point, midway between them, and we can see that the change in velocity goes right through the center. It points towards the center. So the direction of the center, the direction of that acceleration is towards the center of the circle. Now, if you just, let's take a look at number 2 here. A ball, if you want to see more about that, the direction stuff and the formula that's coming up, I do have links coming up, although you can follow this link that's on the screen right now. Just to go to the video, or just wait. A ball on a frictionless tabletop is rolling around in a circle, okay? Yeah, it moved. And it's going around and around and around. And then all of a sudden, we remove this part of the wall. And as the ball comes around, which path does it take? Does it take A, B, or C? Does it take A because we call it circular momentum and it just kind of keeps going around and wants to go around, so it'll kind of scooch over that way. B, since there's no more force there, it goes this way. And C, it will fly away from the circle, as we see. It flies away from the circle. Well, just take a look at these videos of the magic school bus. Okay, it's not a magic school bus. Take a look at this video. Here, notice the kids all going side to side, all synchronized. What's the force pushing them side to side? There is no force. That's just inertia. The bus is making the quick corners. Here's a plane, here's a video of a plane hitting some turbulence. And everybody is seatbelted down. Well, not everybody, but everything that was seatbelted down moved down with the plane. Okay, what caused everything in the plane to go up? Well, the kids go back and forth. Why? Well, they're going straight. It's the bus that is doing the zigzag on the road, and the kids go shimmying back and forth. Okay, and everything in the plane going up. Well, it didn't go up. It just went straight, and the plane went down. The plane went down and hit a downdraft, and the wind was going down, and it pushed the plane down, and everything that wasn't secure on the plane went straight. Well, if the plane goes down, it's going to hit the roof of the plane. That's what we saw. What we saw is a different perspective. We see these camera views that you just saw was from a different reference frame, a reference frame that was moving, a reference frame that is accelerating. And that makes us not understand really what's going on. So what is that acceleration in a circular motion? So if we have a little cup on our dashboard and we turn around a corner, that cup is going to slide out the window. So, but is it really sliding out the window? What's pushing it to go out the window? Well, really, the cup is just going straight and the car is turning. So what looks like from us inside the car of something pushing it along there, nothing's actually pushing it going that way. It's going in a straight line. And this push isn't actually an inertia effect and not a push at all. It's just going in a straight line. That's Newton's first law. Okay, so although when we're there, when we're in the car, we see that we call it a centrifugal force. This apparently pushes things like in a centrifuge. Okay, let's just take a look at this cannon showing this video here. Okay. We saw this cannon firing straight cannonballs. But now if we take the perspective of the camera on the turning reference frame. So we put ourselves in the turning reference frame. This is what we see. And if we see that, we call it a force that's pushing it, and we call it a centrifugal force, or maybe even Coriolis force. But it's just because we're in a different reference frame. And the reference frame is a non-inertial reference frame, and we try to explain things with forces that are actually not actual forces. It's just inertia. So, if a fighter pilot moves too fast in a loop, they can become unconscious due to the lack of flow to the brain. And this is sometimes attributed to the centrifugal force. But what's really happening? So what is all these G-force things all about? What is this all about? So as the pilot is flying along in a straight line and wants to do a loop-the-loop, he pulls back on the stick and the plane does this maneuver. Yay! But this poor guy in there is going to be pushed up with a huge normal force. And that lets him experience like 5 G's of force downwards. And the blood wants to then pool down to his legs. And we don't want that. Why? Because then there's no more blood in the brain. And then you get G-force induced loss of consciousness, or G-lock. That's what they call it. So they wear these tightly strapped and laced up pants, and then there's air bladders in there that fill up quickly because the plane fills it up when they start sensing that there's lots of G-forces, and it squishes the leg really painfully, and it stops any location. The blood can't flow down because there's no room for the blood to flow down. And then you tighten up your gut, and you tighten up the muscles in your chest, and you do very short breathing on it, not to let any relaxation of the muscles so that there's still no place. And you tense up your arms so blood doesn't pool down, because you don't want to lose the blood up in the brain. You don't want to lose consciousness. You wouldn't want to. So let's take a look at a few videos of this happening.
Deep breath. You're on top. Breathe. 1, 2, breathe. Drop the shoulders. Breathe. 1, 2, breathe. Squeeze your legs. Squeeze your butt. Hey, squeeze. Keep squeezing. Keep squeezing. Keep squeezing. Are you there? How you doing? How you doing?
No, no, alright.
Alright, keep your head back. Stay glide bar. Breathe on. You alright, sir? You okay, sir? You doing alright?
Whoa, yeah.
How you feel?
So if you want to see this equation proved, follow this YouTube link. It's on the screen here too. And we have the centripetal acceleration, okay, is equal to v squared over r. Now, this is called the centripetal acceleration. And that means center seeking, not centrifugal. Which means center fleeing. And this is seeking. So this is an arrow towards the center of the circle. So this is the arrow. And this force doesn't actually exist, although we call it that and we talk about it. It's the force pushing us outward of the circle, but it's called inertia. Now, I've been mispronouncing it just so that you can hear it. Centripetal and centrifugal. But really, it's centripetal, centrifugal. Centrifugal, centripetal. Really hard to hear the difference. That's why I call it centripetal and centrifugal. Okay. And so there's our acceleration. You can watch it proved up there. And we have our v. Now, v is just distance over time. And if we're going around a circle once, that is called 2 pi r. That's the radius, the circumference around the circle. Okay? And the time to go around the circle, we call it the period, how long it takes to go around once. So if we take this formula, v, and plug it into this formula, we can get AC is equal to v squared, which is 2 pi r over t, the period, squared divided by r. So this is going to become 4 pi squared r squared over period squared divided by r. The r is down below, but this r then cancels one of those. Okay, so when we put that together, we can get that, oh, this was supposed to be in here, but okay, it's AC is going to be equal to 4 pi squared r over t squared. So there's two ways to calculate the acceleration. The centripetal acceleration, over t squared. Now, which one do you use? Well, this one if you have v and r, and this one if you have the time that goes around in r. Okay, you need the radius of the circle either way. But there we go. And this one is used 90% of the time. I'm going to pause the video here because of my unluck on doing all these things, and we'll continue on with example number 4 on how to use these things next video.